Hi everyone, welcome to this pre-lab talk on the conductivity experiment as part of the CH202 module for second year analytical chemistry. So this experiment is really two different major components covered in this, and both will be concerning conductivity. But the first part of the experiment is going to be an investigation into the conductivity of various solutions and looking at the trends that we expect to see depending on what kind of things we have in solution, and to be able to explain and hopefully by the end of this experiment and what you learned, you might be able to even start to be able to predict how well you would expect one solution, how good the conductivity level is in one solution over another. So we look at that and we look at the factors that govern it. And then in the second part of the experiment, we're going to use conductivity as an analytical tool to be able to analyze solutions. We're going to do a titration which is a little bit more advanced than the titrations maybe you've done before, because unlike previous titrations that you've done where you've titrated an acid against a base and you've gotten an endpoint, here we're actually going to take a mixture of two separate acids, and using the behavioral patterns that we see due to the conductivity, we're going to be able to determine not just one endpoint but two endpoints, and be able to determine the concentration of two separate acids in the same solution, which is something we wouldn't be able to do using something like an indicator that you might have seen before. So as I said, this experiment is broken up into two main parts. There is an initial part, part A, which is basically calibrating the tool you're going to use, and I'll talk you through part A in a minute, but the main two experimental components then are part B and part C. For the post-lab talk, I'm going to separate the post-lab talk into two separate sections, into the part B experimental write-up for the results and the discussion and the conclusions for part B, and then a separate video for the titration for part C. Remembering part A is only a very short piece that we're going to look at just to calibrate the conductivity meter or the probe that you're going to use. So conductivity is not something we think about in solutions very often. Conductivity is the ability to conduct electricity through a medium, and we think about this a lot, in terms of like cables and wires, whether they're metal, like copper wires, or maybe fiber optic kind of wires, but we tend to think of electricity through something really solid. But we don't think about it in terms of, not so much in terms of solutions, but actually it's probably the basic component of human life, is our ability to conduct electricity through the fluids and the cell fluids and the cerebral saline fluids and all the other fluids we have in our body. We conduct kind of electrical impulses all the time, but we're not hardwired with wire or fiber optic cables. So even though this is like very much a kind of an analytically physical chemistry lab, hopefully the things you're going to learn, for those of you who are in maybe a more biologically focused degree, like the biomeds or the biotechs, hopefully you learn a lot from this and that you can apply further down the line in your field of studies in biology. So we're going to look at that a little bit. So we know that some solutions can conduct electricity. You're told the last thing to do when you get if there's an electrical cable going into water is that you put your hand into it, because we know that the water can conduct electricity. Well, not really too much, but what it actually depends on is other things that are present in the water. So the ability of a solution to conduct electricity is governed first and foremost by ions present in solution. So the ions in solution actually carry the electricity from one part of the solution to another part of the solution. And we'll be looking at that in a little second in terms of looking at the probe and how we measure it, but the principles are the same. But when we think about ions, if we think about the fact that ions are like the little soldiers that carry that conduct the electricity from one part of a solution to the other, well then the different types of ions that we have are going to affect its ability to do it. The amount of ions we have dictate the ability of a solution to do that. And so the conductivity of a solution is based on two primary factors, and that is the nature of the ions or the type of ions we have in solution, and also the quantity, the number of ions we have. The more ions that are there, the more that can, the more electricity that can pass through a solution. And in the first part, or part B, so the first experimental part of this experiment, we're going to compare and contrast different solutions that have different ions and different concentrations of ions present in the solution, and see the impact of the conductivity that it has on the conductivity of the solution. So how do we test this? I'm going to show you how we test this and then go back and kind of recap on those two main factors. So you'll see in the video that you're watching for the experimental procedure, and again when you go into the lab, that you'll use a probe that doesn't look all too different from maybe the pH meters you may have used last year. It contains there's a long glass probe. So we have something that looks like a giant calculator here with a little screen on it, and there's a wire that comes off, and then we have a probe. And in that probe, what we have, and you'll see a kind of an outline of this, is it's hollow at the end. There's an area here where the liquid can actually go in, it's hollow. And there's one little, it looks like almost like a square of tin foil on one side here and a square of tin foil on the other. And actually what happens is when we switch this on, we put that then into a solution, the solution kind of goes up into all the different areas. And so if there's ions present in solution that are capable of conducting electricity, the circuit goes down. And if there are ions there that are capable of transferring the electricity from one side to the other, then we see a completion of the circuit. And not only do we see the circuit completed, but we are able to see, because this machine here measures just how well or how unwell or how kind of impossible it is for the solution that's sitting in between these two probes, or these two sections of the probe here, how well it is how well the ions can actually transfer things across. So when we, at the very beginning of the experiment in part A, and I will discuss this in more detail in the post-lab talk, part 1, I will show you how we actually do the calculation to calibrate this and the meanings behind it. But for the minute, let's just see that when we're doing this, one of the first tips to notice is, because this is kind of hollow, now these are about a centimetre maybe wide, that in between each solution or each test you do, you thoroughly rinse that area there, so there's no residual ions left from a previous solution going through, and that's really shown to you in the videos that we're talking about. But let's go back and just maybe scale this up. I don't know where I put my duster. I think my 4-year-old has done a runner with it at some stage. If we scale this up, I'm going to show you how we can look at it in a little bit more detail and show really how the ability of the ions and the nature of the ions and the concentration of the ions really does impact on how well a solution can conduct electricity. So if I was to scale this up, and I'm thinking now of a giant solution here, and I have like these are my two kind of sensor areas on the side of my probe. Okay, and that's going into solution. So I've kind of drawn it in a bigger scale. Now basically, imagine that I have my electricity coming down this side, and it needs to get from here over to here and carry through the solution. Think about the ions almost like little soldiers, able to carry the electricity from one side of the solution from this point to this point. Now, if I know that one ion can conduct one kind of little packet of energy to go across from here over to here, well, obviously, the more of those I have, if I have 10, I'd have 10 times more ability to do the job of conducting the electricity. If I have 1,000, I'll have 1,000 times more. If I have 10,000, it'll be 10,000 times more than just the one. So the more kind of little soldiers I have, because the ions, remember, literally have to go and they have to travel through the solution and go from here, overhit off here, and allow the circuit to continue all the way around as it goes. The more ions I have, the more electricity will get conducted or carried across from one side to the other. So when we look at the various different solutions, we will see and we will discuss how the fact that even when we have the same types of ions, So you'll see in this experiment that we're dealing with, for example, hydrochloric acid, HCl, at a 0.1 molar and a 0.01 molar. So the nature of the ions hasn't changed. We still have the same number of ions present, or the same types of ions present. We have Cl- and H+ ions present. They're all the same size. The nature of them isn't different, but you'll see that when you have a solution that has 10 times higher concentration of ions, you've in or around 10 times more ability to conduct electricity through the solution. So this is a trend that you're going to look out for. So the ability to carry it from one side to the other. The more you have, the more energy that can be carried from here to here, if each one is doing its own little job. So the concentration of ions is the first thing. The second factor is the nature of the ions. And the nature of the ions really is to do with how easily, not that it's not capable of carrying it from here to here, but how long it's going to take, how easy it is for that ion to actually pass from this point of the solution over to this point of the solution here. Now, if you compare something like a H+ ion, it's small, it's light, it's pretty nifty, it can kind of travel through the solution very, very easily. Okay, it's not bulky, it's not heavy, it's, it'll just go through quite quickly. If you compare that as you go down say the first group in the periodic table, and we look at lithium ions, potassium ions, sodium ions, any of those ions in that first group of the periodic table, well, what we know about the size of those ions is that as we go down the group in the periodic table, the ions get bigger and bigger and bigger, and they get bigger and bigger because there's more shells of electrons, so they're bulkier and bulkier. Now, it's pretty much like asking a swimmer to swim from one side of a swimming pool to the other. Okay, and they're carrying something from one side of a swimming pool to the other side of the swimming pool. The more, if you had, for example, a load of little kind of balls Velcroed on one side of a swimming pool and you got them all to swim through, and you said you can take one at a time and they'd swim over and swim back. If you've got somebody who, doesn't have, armbands and swimming rings or whatever on them, they can and they're a decent swimmer, they can go through quite quickly, okay? And they can get over and back and over and back. And say, for example, I have 1,000 little Velcro balls on this side of the swimming pool, and I had to get all of those 1,000 Velcro balls onto that side of the swimming pool and stick them onto the wall of that side of the swimming pool. The more swimmers I have that can do it, the more easy it'll happen and the faster it'll happen. And that we know that by the number of the ions will make a difference there. But in terms of the nature of the ions, as we go through, as we go down the group in terms of the size of ions, we've been moving down, and as I said, from lithium to down, sodium, potassium, as we go down and down the groups, what we'll see is that as they get bigger and bigger and bigger and bulkier, it's almost like getting a swimmer to put on a life jacket and another life jacket and another life jacket. The bigger and the bulkier the ions are, the slower they will be. It's not that they can't do it, it just won't be as efficient. So the nature of the ions in terms of the bulkiness of them will have an impact. The more bulky they become, the less efficient they are at conducting electricity through the solution. So it's not that we won't see conductivity at all, we'll just see a decrease in the conductivity because they're not as efficient. Remember, they are trying to pass through other forces in the solution as they move across and go through. So the nature of the ions has a big impact, but when we're looking at solutions and what types of solutions we have to go even one step further. So we know that the more ions we have, the more efficient the solution is at conducting electricity through the solution. And we know that the bigger and the bulkier, the heavier the ions we have, the less efficient it is. So we could have the same concentration of ions. So for example, we'll see here, and I'll be talking through these in the post-lab talk, but we'll see that we have a 0.1 molar solution of NaCl and a 0.1 molar solution of HCl. Now, we know that when they go into solution, we're going to get a H+ ion and a Cl- ion. So we'll have 0.1 mole of H+ ions, a 0.1 mole of Cl- ions. And then we'll also, when we have the NaCl, we'll have 0.1 mole of Na+ ions and 0.1 mole of Cl- ions. And except for that difference in the cations, the solutions are the same. We have the same number of Cl- ions in both. We have the same number of cations in both solutions, but the difference is that the H+ are smaller, they're more nimble, and they can get through the solution more quickly. The sodium ones are bulkier and bulkier. So even though we have the same number of cations present in solution, given the nature of those cations, what we'll expect to see is that because they're bulkier and they're heavier, they won't be as efficient, and you will hopefully see, if you do your experiment correctly, that there's far less conductivity. It's far less efficient at conducting electricity through the NaCl solution compared to the HCl solution, even though the number of ions is the same. The fact that the nature of the ions is different has an impact. Okay, so that's fine when we're dealing with kind of very polar covalent compounds like NaCl, or like HCl, apologies, that split up to give us ions in solution, and an ionic compound like NaCl, which splits up. But also bear in mind that just because a species solvates into solution doesn't necessarily mean that it dissociates to give ions. So when we dissolve something, and I suppose the more correct term in chemistry is to say that it solvates. When a species goes into solution, we can solvate it. A couple of things can happen. Two main factors. Either it will dissociate down and they will split up and ions will get formed, or what we'll see is that even though the molecules solvate, they go into solution. The individual molecules may pull apart from each other and float around in solution, but they don't necessarily form ions. So something like sugar, which is a kind of it's not particularly polar, it's kind of a polar covalent compound that doesn't really break down to form ions in solution. We will see them solvate into solution. In other words, they will dissolve, but they don't dissociate once they're in. So we don't see a breaking down of the molecular structure or the crystalline structure to give us ions being formed. And so think about what I've just said. Would you expect there to have good conductivity in those solutions? So these are the trends you're looking out for. Also think about solutions that you make up where it doesn't solvate at all. So look at the species as you go through this lab and see, did that even dissolve, or did it just stay as a precipitate at the bottom? If it doesn't dissolve, well then it neither dissociates nor solvates and keeps its molecular structure. If it doesn't go into solution at all, do you think it'll have any ability or any impact on the ability to kind of impact the conductivity of the solution involved? So that's the first part of the experiment, recognizing that the nature of the ions and the concentration of ions in solution impact on conductivity, and looking at the trends that we're going to see in that. So we'll discuss this more in the pre-lab talk. And that's the first section. I'm going to pause this for 1 minute and go and get my eraser or kind of to wipe the board, and I'll be back in a minute. Okay, so I'm back, and now I would like to discuss with you part C of the experiment that we're going to carry out today. And part C of the experiment is, as I mentioned, the very first part of this little pre-lab video was that we're going to use conductivity as a tool to allow us to determine the concentration of two separate acids in a mixed acid solution. So you're going to work with a solution of HCl and CH202-3. You're going to take 50 mils of that solution, and the technique is going to be very similar to a titration you will have done last year, where you monitored to find the equivalence point. You used, instead of using an indicator, you monitored the progression of the titration as you went through using a pH meter. So you had a beaker rather than a conical flask. Conical flasks are used because we can swirl them without risk of spilling out the top. But in this experiment, we have a stirring bead at the bottom, which you'll see in the video. We put our 50 mils of mixed acid in. So it looks something like this. We'll have your 50 mils in here, your starting point of 50 mils of your mixed acid. You'll have a stirring bead at the bottom. You'll have a conductivity probe here sitting in the side, monitoring the whole time. And then with our burette, we'll add in the base mil by mil by mil, okay? And so you'll add, my really brilliant drawing there, but as you add a mil of solution, you'll let it homogenize. In other words, you'll allow the solution to mix to make sure everything is evenly distributed, and then you'll take the reading. Remember, this is connected to an LCD screen here that gives you a conductance reading. Now, I will mention at the end of this pre-lab talk the difference between conductance and conductivity. But for the moment, let me just explain to you that what we're reading here is a conductance value. So if you're reading through the manual, or you are watching this video, or you are watching the video of the actual lab, there is no mistake. There are two separate words. One is conductance and one is conductivity. Now, I will explain the difference, as I said, later on, but for the moment, bear in mind or take note that all of the time you take a reading from this machine here, you are taking a reading called conductance, not conductivity. We have to do a little job to convert conductance to conductivity, and I will explain that before I finish this pre-lab talk. So as we do this and we add it on, you just add your mil, add a mil, add a mil, take a reading, add a mil, take a reading, add a mil, take a reading, and we're going to see shift in the conductivity. We'll see hopefully the conductivity starting to drop, and then it will start to rise again. It's an unusual concept, but we'll see all about it in the pre-lab talk, and I'll explain it to you later on. I want to give you one really important piece of information, and that is this. If you're told to add a mil, but accidentally you add 1.5 mils, that is not the end of the world, okay? What is a big mistake is to say that you did only add 1 mil. The more mils you add, the more impact we will add, the more mils of the base in the burette that you add, the more impact you expect to make on the conductance value of your reading. So if you add 1.5, that's perfectly fine. So if you've gone from, say, 10 mils instead of to 11 to 11.5, that's fine, because on your graph at the end, just make sure that you say, well, I did add 11.5 instead of 11, but this is the corresponding correct value that goes with 11.5. Don't pretend that it goes with 11, because it will skew all your answers. The thing about analytical chemistry is it's really important to stick true to actual values that you use. Don't say, oh, the manual said, so I have to, okay? That's a big mistake and a big, big no-no. Just be accurate to the number of mils you actually add, and keep the corresponding values that you read from this accurate to that. So it's okay to make those slight changes. It's not the end of the world. What I don't want to see is, and I'll know, because if I go through your notebooks, and I will be going around looking at your write-ups, so I'll be looking at them online, if every single student says they added exactly 1 mil every single time, I know you're lying, because it's not, nobody is that accurate in the lab all the time. It doesn't happen. Okay, so be very, very careful and make sure you're monitoring that as it goes through. We don't expect to see any endpoint in this in terms of a change in color. There is no indicator being used. Okay, we are banking on this tool here, this conductivity probe, to be able to monitor the titration and the reactions that are going on within this reaction vessel here. We don't see any color change. You only determine the endpoints when we analyze the data later on afterwards. So Adam, you have to add all 50 centimeters cubed, or all 50 mils of your base as you add through it, and accurately record each of those values, okay? And remember, what you're doing is conductance, not conductivity. I want to talk to you now very briefly about part A, and I'm purposely finishing with this because this is the starting point in the lab. So I want to go back and discuss the probe, the use of the probe, what the difference between conductance and conductivity is, and why we have to look at the two factors and not just the one, and show you how to actually, this kind of is part of the post-lab talk as well for the thing, how to calibrate your probe. So you will notice in your experimental manual write-up that part A says that we have to look at the probe and we have to calibrate the probe and whatever, and we use KCL, to do that. So what we do is, I have my probe here, and it's coming off, and I sit it into a value, into KCL solution. But why do I need to do this? Okay, there's an equation in the manual that says this funny shape K equals 1 over R L over A. And actually, what part A of the experiment here is determining this L over A here. Excuse me, the chalk just always makes me cough. So let me explain what L and A are, what this 1 over R is, and what this value here is. This is our kind of our aim, our goal at the end. This funny shape K stands for conductivity, okay? But it's not the value, as I said, that we get off this here. What we get off here is conductance. So this L and this A are actually the components or the dimensions of the set of this probe that we're going to be using. And so when I dip this into solution, I'm measuring, this meter here has no notion what the size of this probe is. It has no idea what the path length between that is. It's just saying how well the solution has got conducted from one side to the other. But I could put in, I could connect a different probe that had twice the distance. So it's like measuring, you know, swimmers, how long it takes for those 1,000 Velcro balls to get from one side of the swimming pool to the other. But if one swimming pool, if I have two teams and one team is swimming across a pool that's twice the width, that's not fair, okay? So in order to standardize it, we'd actually go back and say, well, you guys had 2 times the distance to travel. If, you know, one person's swimming over each time, therefore, really we should be halving your time to get a realistic view and to standardize it and to normalize it. So this L and this A here are actually the length, the path length between the two kind of metal tinfoily sensors on each side, and A is the surface area that we're dealing with, okay? Now, most of these probes, you'll find that when you all calculate your L over A, they're all fairly similar, but they're not produced by NASA to be like, you know, enormous, you know, that they're all exactly the same and the reproducibility is 100%. There's all slight differences between all of them because of the way they're made. So we have, in order to take this value here and standardize it, so you can take your results and directly compare it with the group doing the experiment across from you, or somebody else doing an experiment on the other side of the world, what we have to say is we recognize that when we're measuring how well the electricity is going, the conductance between solutions, we know that it's going to be impacted by the dimensions of our cell. So in order to standardize it, we take our reading here and we multiply it by these dimensions, and that normalizes it then to a conductivity value. So the first thing we need to do in the experiment is actually determine your L over A here. And then once you have that L over A, they are the dimensions directly linked to the probe that you are going to use for the duration of your experiment. So once you've calculated it once, you will have that for every single reading. So now, when we have our solution, we are going to there is going to be KCl solution, a 0.01 molar, I think KCl solution. Just remembering that I have that right. So 0.01 molar KCl solution, and it'll be in a water bath at 25 degrees. Now it's in that water bath at 25 degrees C, and when you put it in, you'll get it'll kind of fluctuate for a little bit, and then you'll get a reading along here, a numerical value, and you'll take that down. Now, one thing, and I want to drive this home really, really carefully and really make sure you're aware of this. The demonstrators will point it out to you as well. But this, depending on how good the solution is at conducting, it will change units from millisiemens to microsiemens, okay? So millisiemens like that, or microsiemens like that. Make sure when you are taking note of the values that you obtain from your conductance values here, that you note which unit you're dealing with, because you're going to have to do a job later to, particularly in the second part with the titration, you're going to have to make sure that they're all either in micro or all either in milli. You'll get the choice which way you want to go. There'll be no difference, but you do need to make sure they're all in the same unit. So do make sure and keep an eye out every time of which units you're dealing with, and it will say it clearly here on it, okay? So if we think about how, you know, what we're looking at here, what we're looking at is how easy it is for the ions to go from here across to here, okay? And that's basically what conductance is and what conductivity is, how easy it is. It's almost like the inverse of how hard it is, okay, or the resistance. And remember, that solution is going to pose a resistance to those species going from one side to the other. So when we look at this value here, what we're actually looking at is not the resistance, because what we're looking at is the opposite of how hard it is, which is how easy it is, and that is 1 over, or the reciprocal of our resistance. So the value here is the value you get off the screen. It's 1 over the resistance. So now, for the KCL, you are given, you're going to be given a literature value, and I'm not going to work it out for you. You need to go through the manual, you need to find it out. But for the KCL and the KCL alone, you are actually given a numerical value to plug into the equation. You will also have the reading read from the meter. And the final thing you need is what's called your cell constant, which is L over A. Now, you do not need to know L or A independently. You need one numerical value that represents L over A. So if you look at that, what we're going to say then is that L over A, or your cell constant value here, equals the given value for the conductivity divided by the meter reading for the KCL, and that gives you your cell constant value. Going forward then, what you will need to do, and I'll mention this in the pre-lab talk as well for part A, is that every time you took a reading for the various solutions that you're comparing and contrasting, remember that the reading you're getting is only ever a conductance value, okay? That is conductance here. To convert conductance to a standardized format of conductivity that can be compared to anybody who's using any different equipment, you need to multiply it by your cell constant here. And so when you're presenting your data, you need to take the reading that you get for that particular solution and multiply it by this cell constant. Now remember that you're using the same probe for the duration. So once you've calculated this once, they are the dimensions that you're using all the way through. And so the conductivity values that you should be discussing and determining are the readings that you get from the meter multiplied by the L over A, or the cell constant that you govern for your experiment, and that gives you then your conductivity. But all the readings you get at every stage in this experiment are conductance values, and they all need to be converted to conductivity values here by multiplying by your cell constant. One last point that I want to point out is that when we are comparing and contrasting the different solutions, you will notice that all of them are being done in a water bath. They're all, every solution, the conductance is being taken at 25 degrees for all of them. And that's a pretty simple concept, because if you think about it, if we want the ions to move from one part of the probe to another part of the probe over here, well, the more energy we give them, the easier that is to happen. So if I was to test one solution at 10 degrees and another solution at 40 degrees, even with exactly the same ions in solution, I would have different conductivity values, the more energy that was available to it, okay? But if I want to compare and contrast different solutions, I want to make sure they're all on a level playing field. They all have exactly the same amount of external energy available to them. That changing the energy is not in any way influencing the conductivity of the solution. I need to make sure I compare and contrast them all at the same temperature. So for that reason, part B of the experiment, which is the comparing and the contrasting of the different solutions, it is imperative that you make sure to try and minimize variations from external forces, such as differences in temperature, that all the solutions are tested at a similar temperature, and we've gone for 25 degrees. For that. It's not so important for the conductivity titration, because it's the same solution. They'll all be at the same solution. They'll have been left out. They're at room temperature. They're both at the same temperature. So we're looking at fluctuations in conductivity, which are really only going to be dictated by the nature of the ions in the solution. Not that we're comparing and contrasting different solutions. We're testing the same solution the whole time. So it's not so important. So make sure when you make up your solutions that you get them straight away into the water bath, and make sure, and the probe will actually tell you, these probes that you're using have a built-in thermometer with them. Make sure they're all to within 0.1 of a degree of each other. If one is only 22 degrees and the other is, at 25, you're not making direct comparisons of both on a fair and level playing field when you want to test the conductivity. So I leave it at that for the pre-lab talk. I will say that this is one of the longer of the experiments. The other 2 wet labs after this aren't anywhere as long, and the pre-lab talks aren't so long. But hopefully I've clarified a little bit of what's going on. I will be floating around the labs if you have any questions, and the demonstrators will also be there. But I would strongly advise that you come to the lab familiar with everything, ready to go, have a go at the calculations to determine how much of each species you need to weigh out. You will have seen how to go about approaching that in the stoichiometry workshop that will be done with the Beer-Lambert law. Best of luck.